All right. So far, we've done a study of the device physics. We understood how the devices work, and we've developed some model. Of course, what we've done is not a thorough study of the device physics, but we've gone from the physics of it to an equivalent circuit. And this is what we did last time. So now the question is that once you have this equivalent circuit, what do you do? How do you analyze it? I mean, it's really an abstraction, right? We've gone from, well, essentially all of our sciences are abstractions. But it's another level of abstraction where you actually create something that's defined in terms of currents and voltages. And we saw that, for example, we had the large signal model for the transistors, and we had the small signal model, which was a linearized perturbation model. The question is that how do we analyze these things? And what I'm going to do quickly right now, we are going to quickly review some of the underlying methods for circuit analysis. This is not a class on circuit analysis, so this would be a very brief review of what we cover, for example, at Caltech in W44 or things, and to some extent in 45, but just very brief review of that. So the question is that if you have a circuit, meaning that a network it's a graph that allows you to relate the currents and voltages to each other. And we know what there's one condition that needs to hold for it to be really called a circuit, which is that the dimensions of that should be much smaller than the wavelength. If you have something like that, there are different methods of analysis. So the most general method of analysis for a circuit is essentially what we call the nodal analysis. So very quickly reviewing nodal analysis was that if you had a circuit, a network with n nodes, so let's say you have n nodes, let's just make it some sort of an example circuit here. So let's say you have something like this. Now, let's say you have a network like this. We can give them names. I can call them G1 or R1, C1, C2, G2. You can call this G3, C3, L3. And then this can be GM. Let's say this is GM related to this V pi. And you can see this is kind of starting to resemble a model of a transistor, of course, with certain kind of load. So we don't make an arbitrary circuit. We make something that's relevant. So this is, let's say you're given this circuit. So this is your I in. Let's say I in. Now, if you're given this, how do we analyze this? There are different ways to analyze it. The most general method of analysis is called nodal analysis. And the method basically has the following steps and procedures. So first you define one of your nodes as the reference potential. So you define one of the nodes. Usually you want it to be one that has the most connections to it. So the idea here is that assumption is that all of them are actually physically connected. And we call that ground. Now, this by itself, so this is a mathematical abstraction, right? We can say this is the reference potential. This is zero potential. Now, this is not necessarily true from a physical perspective, in the sense that if you have a large physical circuit, different parts may be connected through a piece of metal, but that connecting metal may have resistances. So there may be resistance here, there may be inductance here, there's capacitance to ground, there are all sorts of other parameters. And that means that you have to differentiate between a mathematical abstraction and a physical model. So if you are, for example, in the lab, you may have everything connected to some big sheet of metal. So that's my ground. It doesn't mean that every point on that ground will have the same potential. So you have to think about it. Or if you're making a chip, you may have a wire bond connecting this pad to a larger piece of metal and that pad to a larger piece of metal, and you may say all of them are ground. Now, if you assume that they're identical potential, you've made an assumption here that can lead to errors, especially at high frequencies and things of that sort that we'll see. But now, from a mathematical perspective, this is what it is. Now, in those cases, in those scenarios, if you, for example, have something like this, if let's say you have a resistor here and a resistor there, then this becomes a separate node. So you really treat this as a separate node. And if there's a resistance intervening between these guys, this becomes a separate node. So what you may view as there's no global ground, really. in that sense. Although a lot of times we refer to it, we need to really think about it as something that's more of an abstraction. But anyway, so let's go back to the mathematical model, the simplified mathematical model. So we define one potential as ground, or 0. So let's say your circuit has n plus 1 nodes. So now you're left with n nodes. In this case, how many nodes do we have? What are nodes? Nodes are defined as connected metals or conductors. So for example, this whole thing is a node, right? Or in that case, this is a node, or this is a node, and this whole thing was a node, right? We defined it. Now, we define a voltage for each one of the nodes. So we call this, for example, V1, the voltage here, V2, and V3. Now, if you have something like this, and what you see here is that we have only linear elements right now, right? The way we've defined it is linear. So, and then nodal analysis really by itself is only applicable to linear circuits. So for example, if you have a small signal model, you can apply the nodal analysis. If you have a large signal model, you cannot apply it in its current form. So we'll talk about that in a second. But now let's say you have these things. So what you do, you write basically KCL, Kirchhoff current law, at each one of the nodes in terms of the voltages of the nodes. So we can do it different ways. We can actually write them in terms of currents. So we can give these currents names. We can call this I1, I2, I3. And this would be I3, I guess I4, I5, I5, I6, and I7. If I write it this way, you can write KCL, right? The KCL here would say that I in equals I1 plus I2 plus I3 equals I in. That's the Kirchhoff current law, which comes from conservation of energy and, conservation of charge, not conservation of charge, and the fact that the dimensions are much smaller than the wavelength, which basically from Maxwell equations you can show easily that it shows that there's no charge accumulation on the node. You need that second condition that the dimensions are much smaller than the wavelength for this to hold. Otherwise, you can have charge accumulated on the node, at least temporarily, or charge being drawn out of the node. There's no net charge accumulation on any of the nodes. And that comes from Maxwell equations if you essentially assume that the speed of light is infinity, which means that dimensions, which is another way of saying that the dimensions are much smaller than the wavelength. So for us, from a circuit perspective, the assumption is that the speed of light is infinity. The propagation happens instantaneously, and that simplifies the Maxwell equations to what turns out to be the circuit's equations. So that's one. And the other one is basically you can write it as negative I3, so all the currents leaving that node, I4 plus I5 plus I6 plus I7 equals 0. So you have two sets, two, and then there's a third one. Well, we define this as a node, so this wasn't, I should not have called this I3. I should have called this I3 and this I8, and this would be I8 if I wanted to deal with that as a node. So this becomes I8, and then I will have another equation from here that says negative I3 plus I8 equals 0, which would then equate I3 and I8. So you can see that I have three equations here. And now we can express these in terms of the voltages. How do we express this in terms of voltages? So for example, we know I1 is what? G1 V1, Ohm's law here. Or for example, I2 is going to be C1S V1, and so on and so forth. And you can write all these things. So when you write all of those, what you will see, for example, is that you will come up with a, so we can actually try writing these in this form. You can actually write it as a matrix, what we call a Y matrix, multiplied by V1, V2, and V3. And in that form, so for example, here, this equation has, so let's write these equations in this form quickly. So we have G1, V1 from this one. We have C1S, V1 plus, now we have this one, this current, which is basically V1 minus V2 times C2S. C2S times V1 minus V2. That is the current across this one, because it's this voltage minus that voltage times the admittance of that element, which is C2s, equals I in, right? So that line in the matrix form would become G1 plus C1s. Actually C1 plus C2s. And then the second term would be negative C2s. And the third term would be 0 because there's no V3 in that equation. And then on the right-hand side, you will have the I in for that. And similarly, you can write the second equation, which is this one, really. I just wrote them in the wrong order, which basically says that this current, which we calculated to be C2s, negative C2s, V1 minus V2, plus now this current, which is basically going to be G2 times V2 minus V3 equals 0. So that would produce a term for V1 that's negative C2s. That would produce a term for V2, which is basically G2 plus C2s, right? And then you get a term for V3, which is negative G2 from that one. This is basically really this equation. I've reordered them here. And then the last equation, which is this one, the longer one in the middle, would give you what? Would produce that negative, so this current is negative G2, V2 minus V3. So that's that current, negative I8, plus I4, which is going to be now GM V pi. Now, what is V pi in terms of the node voltages? Can we express it in terms of node voltages we have? V pi is just V1, right? Because it's this voltage. So GM V1, and then you have so you have then I5, which is basically now G3 V3 plus C3S V3 plus 1 over L3S V3 equals 0. So what that gives you here, you have a term for V1, which is plus GM here. And then for V2, you have so the term you have for V2 is negative G2, right? That's the only one that you see. And for V3, you have a whole bunch of stuff. So you get negative G2 from this one. You get you get positive G2 because this is negative times negative. G2 plus G3 plus C3S plus 1 over L3S. So this is what we call the Y matrix, right? And you're familiar with that. This is called the nodal analysis. This is the admittance matrix. Now, it has certain interesting properties. Now, if you didn't have any dependent sources, this Y matrix would be symmetrical. In other words, if your GM was 0, you notice that it's symmetrical, right, with respect to the diagonal. Now, the other thing that you find interesting is that the diagonal elements are all the conductances attached to the node in question. So, for example, this is element 1, 1. For node 1, if you look at all the admittances attached to it, it's G1, C1, and C2. G1, C1s, C2s, really, more accurately. Now, or for example, for this node, you have G2 and C2 attached to it. Or for this node, you have G2, G3, C1, C3s, and 1 over L3s. So the diagonal elements are essentially the elements attached to those nodes. And the off-diagonal elements, again, not counting the dependent sources, are basically the negative of the element directly connecting those two nodes. So for example, nodes 1 and 2 are connected through C2s. So you get negative C2s, 1, 2, and 2, 1. Or elements 2 and 3, nodes 2 and 3 are connected through G2. So you get negative G2 here. Now, the dependent sources make this asymmetrical. And that's basically, these are the things that account for the action of the transistor, and those are the things that make the network what we call non-bilateral. I mean, it can make it unilateral, or can make it asymmetrical in the sense that it behaves differently in one direction than the other direction. And we'll see how that behaves. Now, the nodal analysis, and you could do something else if you wanted to simplify this. So this is kind of like a little bit of a larger form. We could have combined these two and treated them as one thing, one element, with the value of G2 plus C2S. I'm sorry, no, G2 really times C2S divided by G2 plus C2S, because these are two conductances in series that behave like two resistors in parallel. So you could take that and then combine them and treat them like that, and instead of a 3 by 3 matrix, you would have gotten a 2 by 2 matrix. But then you wouldn't get the information directly for node V2. And if you're not interested with what's happening in that node, that's fine. But you can always calculate. If you know the voltage V1 and V3, you can always extract the V2 from those two, because it's a voltage divider between that conductor and the capacitor. So that's fine. So this is kind of like a very standard way of analyzing circuits, right? I mean, this is the fallback. This is what I call fallback, in the sense that it solves any network you throw at it. The key to it is that it's actually, and if you want to solve this, how do you solve this? So basically, this is the Y matrix, and then this is what we call the voltage vector, the vector. So this is a matrix. I'm putting a tilde on top of it to emphasize the matrix. And this is the vector of a stimuli, IS. So the compact form of this expression is something like this. So these are the unknowns, and these are the stimuli. These are the inputs to the circuit. So how do you solve this? Of course, the easiest way is you've reduced it. I mean, like most of 80% of math, once you reduce it to linear algebra, it's solved, right? So you've reduced it to linear algebra, and so you invert the matrix, and you apply it to the vector stimuli, and that basically produces all the voltages. Now, if you're interested in one particular one, you can derive that. But now, the key point about this is that if you look at the inverse of y, how do you define it? It's the cofactor matrix divided by the determinant of y. Now, the key point is that, first of all, for this inverse to exist, the determinant of this thing needs to be what? Non-zero. Right? So this matrix cannot be singular, as we know from linear algebra. And in other words, this inversion blows up when this determinant is 0. And we will see that's important because it means that the roots of the determinant so y of s, so when they are 0, the frequencies at which they are 0 define the poles of the transfer function. And we will see how we derive them, and we find them, and we'll use them in the circuit design, and we take advantage of them. Now, and if you, of course, want to find and you can also see that if you're trying to find the relationship between an input and an output, you, of course, depend on both of these parameters. So it not only depends, and that would be the definition, the frequencies at which those become 0 are what we call zeros, and that would depend not only on the Y matrix by itself, but the definition of the input and output. And you will see when we get, for example, the generalized time and transfer constants method, when we talk about that the poles of the system, the poles of any transfer function, are functions of the network itself, but the zeros depend on the choice of the input and output. So if you choose a different output, you get a different set of zeros, but not a different set of poles. So for example, you can have one input and say, well, I'm taking my output from this node, and you will have the same set of poles, but different set of zeros than you would have if you take the output from a different node. And we'll see this in detail, and that exhibits itself. But really, it's coming from the fact that the poles are really determined by the Y matrix, not the choice of which one of these voltages is the one that you're interested in. But if you want to do the zeros, you will need to take that into account. That choice would matter. OK. Any questions on that? So this is a very basic analysis, but it has a major limitation. I mean, this is a very powerful analysis, but it has a major limitation still. What is that major limitation? Well, there are several different limitations from different perspectives, but what is the major, the most glaring limitation of this thing if you wanted to apply this to the devices that we've developed so far? It's linear, right? And those devices are nonlinear. This relies on linear algebra. So, and the other question, so that's correct. That's the most glaring limitation, and we'll talk about that in a second, how we deal with that. Now, the other limitation of this thing is that this is not particularly conducive to design. This is not particularly useful for coming up with new design. It's good if you want to analyze something that you already have. And even in that case, it's not particularly good for human beings. It's very good for computers, because computers are really good at dealing with the large matrices of numbers and inverting matrices and all those things. And we are not. Okay? So the key question is, but what is it good for then? Well, it's good for writing computer simulators. And that's what the computer simulators that you will use in the class, are essentially using variations of this thing. And we'll talk about how they use these variations in different cases. Depending on what kind of analysis you do, they use it differently. But they use this, essentially, this nodal analysis as the basis for the subsequent analysis they do. So now the question is that, let's say you're interested in the behavior of a circuit, but you are trying to kind of model something with a nonlinear device. Let's say you have a transistor or something like that. And then the question is, how would you use this? Can you possibly use this? Let's say you have a transistor and it's being driven by a square wave. And you're trying to find out what the output of that thing looks like. Let's say the computer simulator is trying to do that. Can we think of a way of using this still to model that nonlinear behavior? Can we think of a way to have our cake and eat it too? Any suggestions? Any thoughts? Yes. Okay, so replace the transistor with some equivalent linear components, and then do what? Okay, so if you do the linear analysis, then you have linearized it, right? So you've suppressed all the nonlinear behavior, it sounds, right? Okay, but that's a good starting point. So let's say you have a transistor. We talked about small signal model, right? So let's say you have a transistor and it's operating at some, so let's say, very simple model. I mean, just like, let's say you have a bipolar transistor or MOSFET. It doesn't matter. And then we will talk about these stages in detail soon. But let's say you have something connected with a resistor to some supply, some VDD. And then you have some input and an output. So this is V in and this is V out. Now, this is obviously a nonlinear behavior transistor. Let's say the model, you want to use the quadratic model or a more complex model. There are more complex models that the computer simulators use, but they're all nonlinear, right? So you have this nonlinear behavior between the ID and VGS, and it also depends on the VDS and all of that stuff. So how do you do that? So one of the things is that, let's say you have applied some input DC voltage to it, and then you have an AC voltage on top of that. So let's call this VGS. And then this is VGS lowercase. And you are trying to find out, but this is not necessarily small. So let's say this thing, let's say it's a square wave. How would you deal with that? So let's say you start with a point, say, well, at this point, the beginning of this thing, this is the voltage. So you can actually say, okay, I am thinking about this as a DC operation point that I've been at. Let's say I start my simulation at this time. Say, okay, this circuit would be at some operation point. You can find what the current and voltages would be, right? You can solve those equations. This is a simple set of equations, just like to solve it locally and statically. So you basically solve it. You find what the ID, the DC current would be, or the total current, and the V voltages are. So once you define that what ID and the VGSs are, so you can actually define things like GM. So you can say this is ID versus VGS. And say, OK, at that point, I'm here. Right? And then what do you do with that? Say, well, OK, I'm here. So now I linearize it around this operation point. I do a perturbation. I say, OK, this is my GM, the slope of this line. Or this is my RO for the VD, if you have the slope of the, or you can basically have the other curves. Let me just draw them. You can say this is basically ID versus VDS for that operation point, and you have this slope, and then this slope is, of course, 1 over RO. Right? So you find these parameters. So from that, you develop what? You can calculate a small signal model. Right? And your small signal model is not limited to these static, low frequency parameters. Right? You can also calculate the capacitors and all of that. So you develop a small signal model at this operation point, at this particular operation point that you found. Now, you use that small signal model to say, OK, now if my input is changing this way, how is the output going to change? So how do we do that? We use the nodal analysis at this linearized point, right? Use the nodal analysis to estimate what the next step of the circuit is. So in time domain, you have found one operation. Let's say this is one of the voltages you're interested in, the node voltages, right? Or 2 voltages. So you have defined V in and V out. And then you say, OK, I'm going to take the nodal analysis. So now I use the nodal analysis to solve the circuit, linearized circuit at this point. And say, OK, well, the linearized circuit is going to behave this way and this way, for example. I don't know. You can calculate it, right? But you won't take it all the way down. You say, OK, let me take a small step. You say, OK, I'm taking a small step. I'm only going this far. So now my operation points have changed a little bit. So from this change now, I can come and calculate a new set of operation points. So you say, now my operation point has moved here and there. And as a result, my GM has changed to this new value, and my RO has changed to this other new value. So I update the parameters of my small signal model, and now use that to come up with a new estimate for what it's going to be doing. So I'm going to throw this away. So, well, you know what? It looks like it's not going to go that fast, or it's going to go faster. It's going to go like this and that. And I take another step. Now, how do we decide on the size of the step? We say, OK, the change in each step should not exceed a certain minimum. Certain maximum, sorry, certain maximum. And that sets the tolerance, one of the tolerances. So you take this stepwise iterative process, and you constantly solve the nodal analysis. You do a nodal analysis repeatedly on this modified, updated operation point that's coming from the nodal analysis that you've already done. So that's how the simulator actually works. Now, we are not going to design circuits this way. But that's how the simulator works. That's the underlying method for the simulator. I mean, this is a very simplified picture. There are lots of analysis. There are a lot of details in there. But that's the essence of it. So this analysis is useful for even the nonlinear system because you constantly recalculate the operation point from this and evaluate it based on the previous day. And every so often, if you see a big jump, what happens is that you take a step and say, oh, OK, well, a big thing happened. Big change happened, bigger than my maximum range of variation. Well, you take a step back, you take a smaller step. And if that's still too big, you take a step back, you take a yet smaller step. Till you get to the simulator gets to a point that it reaches that level of change, maximum level of change that you're permitting, and then it maintains a certain level of accuracy. So that's what we call a transient analysis. Okay? So that's the basis. But now, from a circuit design perspective, nodal analysis is not particularly useful, in my opinion. It's the last resort. We should not use it unless we absolutely positively have to. So we make a lot of effort in not using nodal analysis, because there are other things that will allow us to see what's going on. So what are those things? So some of those things are the classic theorems of the network theory. So what are some of the classic theorems of the network and circuit theory? So you have the most prominent one, of course, for a linear circuit is superposition. So it basically says in a linear circuit, the effect of sum of stimuli is the sum of the effects of an individual stimuli. Now, how do we calculate this? So the effect of the sum equals the sum of the effects. That's superposition. I mean, there are many, many. And the necessary and sufficient condition for superposition to hold is what? Linearity, right? So if you have something that's linear, superposition holds. If you have something where superposition holds, linearity, it's linear. So how is it applied in circuits? Again, to refresh everyone's memory, you remember this. You may have a network. So let's say you have a network with a bunch of current sources and voltage sources and dependent sources and of varying kind, and elements, capacitors, inductors, resistors, what have you, whatever. And they're all connected to each other somehow, in some way. And we are interested in certain behavior of certain parts of the circuit. And let's say we are interested in certain voltages or currents. What it says that if I am, for example, interested in this current, Ix, I can calculate Ix by doing what? By setting all, now, and this is the key part, again, I'd like to emphasize this because this can lead to a lot of problems if not paid attention to. This, you null with 0 all independent sources. Only the independent sources, not the dependent sources, because dependent sources are kind of like elements, like they behave like individual elements, conductances, resistances, and all those things. So you take the independent sources, you null them. What does it mean to null a source? Again, to refresh everyone's memory. Nulling a voltage source, what does it mean? A voltage source with 0 voltage is what? A short circuit. A current source with 0 current is what? An open circuit, right? So we open all the current sources, we short all the voltage sources, and we keep one at a time. You look at what this current is, so you get Ix1. And then you do it for second one, you get Ix2. So then total Ix is going to be sigma Ix n. N equals 1 to capital N. So you calculate this Ix, and sometimes it may be positive. For some of them, it may be negative. You do an algebraic sum. That's the definition of superposition, how superposition works, right? You do not do this to the dependent sources, obviously, just to emphasize. And then you do that. So that's a superposition. So that's one of the theorems that's helpful in understanding the effect of different things. We will not use it that much directly, but we will use some of its implications. The other ones that are quite interesting and important to remember is Thevenin and Norton theorem, Norton equivalence. So what Thevenin and Norton say is that if you have a network like this, and it's made purely out of linear elements, they could be sources, they could be dependent, independent sources, inductors, capacitors, resistors, what have you. Now, and it has two terminals, just two terminals, namely one port. Okay? What it says is that this whole thing can be modeled. So Thevenin equivalence says this can be modeled as a source, in general, a voltage source, in series with some impedance, Z, and Norton equivalent, so this is the Thevenin equivalent, Z equivalent, let's say, and V Thevenin, and then or a current source in parallel with the same Z equivalent, which would be, well, one Y equivalent, which would be 1 over Z equivalent. Let's say equals 1 over Y equivalent. and this is I Norton. So it says that if you take a box, if this is a black box, with purely electrical measurements, you cannot differentiate. And purely electrical means currents and voltages, just current and voltages. There are other things that you can differentiate these things, right? For example, if you put them on an X-ray, you can differentiate these things. Or if you look at the temperature, you can see that this one is warm and this one is cold. Or if you look at the magnetic field, for example, you will see that this has magnetic field around it and this one doesn't have magnetic field. So when we say they are indistinguishable purely by voltage and current measurement, not by other means. So it means that all of this thing can be reduced to something like this. Now, what are the values of these things? So there are a couple different ways to think about it. One is that Z equivalent, so what is V Thevenin? V Thevenin, which is also shown sometimes better, I think, as VOC, V open circuit, is the voltage you experience here if you don't load it, if there's no current flowing. If you keep it open circuit, what's the voltage you see here? Now, that voltage may be a constant, may be a variable voltage. So this V equivalent doesn't even have to be a constant. It can be something, you can say V equivalent is this, or VOC looks like this versus time. Or same thing for I Norton. And for I Norton, or better, ISC, as you can imagine from the name, this would be the current that would flow if you short-circuited this. And this would be this current. So ISC. And again, ISC doesn't have to be constant. It can be a function of time or a function of frequency. So in this case, it can be a function of frequency. It can have certain behavior in frequency or certain frequency in time or whatever. So in general, it can be some voltage, but it can still be represented as such. Now, how about the Z equivalent? What is Z equivalent? Well, Z equivalent is basically the impedance seen looking between these two terminals when all the independent sources are nulled. Again, we know what that means, nulling the source, setting its value to 0, meaning shorting the voltage sources and independent voltage sources, not the dependent ones, and opening the independent current sources. Okay? So that's the T equivalent. So that's the Thevenin and Norton, again, review for you. So there are two other theorems that are probably, so Thevenin and Norton are useful. I mean, so we use them from time to time because we want to think about a part of the network as an equivalent when we deal with the rest of it. Then the other ones that are quite useful, one is source transportation. So we've already used it in this class. Which basically says, for example, if you have three nodes, nodes 1, 2, and 3, and let's say if you had a current source, there's a current source version and a voltage source version. So if you have a current source, it can be dependent or independent current source. You can actually replace this by removing this and putting the same current source of the same value, I1, going into the third node and out of the third node. This way, the total current leaving or entering each one of these three nodes remains the same. Because the same current I1 is leaving this node, the same current I1 is entering this node, and the total net current of 0 is entering or leaving this node. And then there's a voltage dual to this, which is basically says that if you have two nodes and a voltage source here, you can actually remove this and put this the voltage source, two voltage sources here of the same value. I like to think about it as toothpaste. You squeeze it out and it goes into these things. Like a paste that goes into tubes. But anyway, so that's useful. We use this where? You remember when we were trying to convert, for example, the pi model to T model? We use that theorem. There's another theorem which is perhaps the most useful and most commonly used theorem in electronics design, which we actually don't explicitly say it, and most people don't mention it explicitly, is the source substitution. Substitution theorem, or for short. The source substitution theorem is actually the most commonly used theorem in electronic and circuit analysis for active devices, which basically says if so at some point in this network, you, for example, you have an element where you see a voltage. So you measure the voltage across this element, right? You can replace this element, you can take it out, and replace it with a voltage source of the same value. Now, if this value is a constant, you replace it with a voltage source of constant value. You can say if it's always 2 volts, you can put 2 volts. If that voltage source is if that voltage you measure is a sinusoid of frequency of 12 gigahertz with a phase of 45 degrees, you can replace it with a source of 12 gigahertz and amplitude of whatever, 1, and phase of 45 degrees, and nothing will happen. But it says that if you replace it, nothing else, nowhere else in the circuit changes. The same thing is true. It has a current dual, which basically means that if you saw a current through a branch to be something, you can replace it with a current source of the same value, and nothing else changes. Right? Which makes sense, because everyone else from the outside sees the same voltage or same current, so nothing is changing. And you can actually prove it formally. None of these we are going to prove. If you're interested in the proof, you can see the 44 lectures and things of that. So this is basic. Why is this useful? We'll see this frequently. This is particularly useful if you have cascaded stages of amplification. So if you have amplifiers that are cascaded, the input of one is the output of one is the input to the next one. So this is your input, and this is your overall output, and this is stage 1. And all those things. So now what happens, of course, is that each one of them represents a source impedance and has a load impedance. And we'll talk about these in more details. So let's say there's a source impedance here, and there's some sort of a load equivalent here. So what it says is that I can replace all of this thing with just the voltage that I will see when that source is running. So I can put an ideal voltage source here of this voltage and calculate the gain of this thing. What this does, it allows you to abstract away different stages and analyze them independently. Again, we'll see examples of this. So, but when we see them, I want you to know that this is coming from the source substitution. I will point it out too, if I remember. All right? So those are some of the key theorems behind this. Now, there's one more thing that we generally need to talk about to make sure that we're on the same page, and that's the concept of 2 ports, right? So you can actually have a box that looks like this. And again, we try to actually stay away from 2 ports to the extent that we can in design. Some people just use it extensively. I don't think it's great. But we use it in some of the analysis that leads to, or understanding of the analysis that leads to the design. So what is a 2-port? So is it some box with 4 terminals? Is any box with 4 terminals a 2-port? See, remember, this was a 1-port. When we had a box with 2 terminals, and if this whole thing was much smaller than the wavelength, meant that there was no charge accumulation, net charge accumulation inside. You may say, what about a capacitor? Capacitor doesn't accumulate net charge, right? You have positive on one side and equivalent amount of negative charge on the other side. So if that's the case, then this current is identically the same as this current at all times, if this is a circuit. And of course, if this is comparable to the wavelength, this doesn't have to be true, right? You can have a transmission line, the current goes in, and it sometimes takes some time for it to come back up. But if it's the dimensions are much smaller than the wavelength, these two are always the same. Meaning that's another way of saying speed of light or propagation speed is infinity. Okay? So is any box with 4 terminals a 2-port? Because we define this pair of terminals as a port, right? Is anything a 2-port? Is every arbitrary 4-terminal box? No, right? So what is the condition for a 2-port? So it's a subset of all the 4-terminal boxes that makes a 2-port. What is that subset? What's the definition of that subset? What kind of subset will satisfy that? Any thoughts? Well, this current has to be identically equal to that current. And this current has to be identically equal to that current. So for this to be a port, this is the condition you need to satisfy. And if that condition is satisfied, then you can write certain set of equations. You can simplify this into a 2-by-2 matrix representation. So you can, for example, and there are different boxes. For example, you can start with currents as stimuli and measure the voltages, and that would produce the Z parameters. So for example, if I start with, say, this is I1, and this is I2, and this is V2, and this is V1, what I can say is that I can write, so the inputs or stimuli are I1 and I2, and then there's a matrix that operates on that to produce V1 and V2. And that matrix is called Z11, Z12, Z21, Z22, and this is called the Z, these are called Z parameters. And they're easy to find. I mean, and we'll talk about them in a little bit more detail later when we need them. For example, Z11 is the ratio of V1 to I1 when V2 is 0. I'm sorry, when I2 is 0. Right? You set I2 to 0, meaning, and how do you set I2 to 0? How do you set, what happens when you set a current source to 0? Open circuit. So basically means that it's the ratio of this voltage to this current when the output is open. So you open this from a practical physical perspective, and you measure that. So that's how you measure Z parameters. Now you can imagine there's a Y parameter, set of Y parameters, right? So what are the Y parameters like? Well, that's if your stimuli are voltages. So if I replace these things with voltage sources, V1 and V2, and monitor I2 and I1. So in that case, my stimuli, my inputs are V1 and V2, and my outputs are I1 and I2. And those parameters are Y11, Y12, Y21, Y22. And there's a relationship between these, but it's not a one-to-one relationship that Y12 is equal to 1 over Z12. It's a matrix relationship. Why? Because, for example, if you're trying to calculate Y11, what is the setting? V2 needs to be 0. When you set V2 to 0, what are you doing? A voltage source with a voltage of 0 is a short circuit. So this is a different setting. You're measuring the properties of the input when the output, for example, is shorted versus open, or when you do the trans parameters from V1 to I2 or V2 to I2, these diagonal, off-diagonal elements, those would be affected by whether or not you're shorting or opening the output. There are all sorts of other parameters. There are the TT parameters, ABC, S parameters, things of that sort. So we will deal with them when we need them. Okay? So this is a very, very quick high-level review of the circuit and network theory that just we want to make sure that everyone's on the same page before we move forward. Any questions?